Yeah, hi guys, welcome to the present session. So in this video, we are going to see the MHSET part 2, okay, that is electronic science paper 2, and part 1 already did in the previous video. So whoever the candidates wants that video, so you please once access this YouTube channel, then you will get all the videos regarding this different electronic science questions, guys. Okay. So before going into the main content of this video, okay, the candidates, if you're not yet subscribed, okay, so please subscribe the channel, okay, and then tap the bell icon to get the regular notifications. And at the same time, so please share this group link, this YouTube channel link in your respective groups also, right? So now while coming to the present content of the video, and it is paper 2 electronic science in 2021 conducted by the MHSET it is. And in this question paper already we saw the 4 questions, and while coming to the next question, so that is the 5th one, mobility of electrons for the silicon, okay, at intrinsic at 300 kelvins. So regarding this topic already we discussed in the part 1, so that you may check down, and here the few values also I given here. Mobility of the electron for the silicon, it is 1400 centimeter square per volt second, germanium 3900, and the mobility of the holes, so it is 450, and mobility of holes in the germanium is 1900. Okay, so as per this one they are asking the silicon, okay, mobility of electrons in the silicon, that means mu, and they are asking, so it is 1400 centimeter square per volt second. So you can take 1400 means nearly the equation, the expression is 1350 centimeter square per volt second. Okay, so actually the units of this one is centimeter square per volt second. Okay, they mentioned wrongly here as a second, but anyhow, so we can take here option A is the correct answer. And all of you please remember the expression, values for the remaining, just like the germanium mobility of electrons and silicon mobility of holes, as well as the germanium mobility of holes. Fine. Okay, so now while coming to the next question, that is distribution of implanted impurity ions by ion implantation method is what? That means generally in the VLSI, that means in the IC fabrication process, ion implantation is a one of the step. Okay, so where we will get this ion implantation step is that, so let's have a look here. Usually the different steps we will follow in the IC fabrication. So out of the different steps, the first one we will take the substrate. Okay, we will take the substrate like this, and on this substrate we are going to take the oxidation, that is silicon dioxide layer, and on this layer we will get the photoresist material. Okay, and after exposing to the ultraviolet rays with the help of the mask and all these things, we are going to form the windows here. That means basically wherever the after etching process the windows will be formed. So windows are formed to do the further diffusions. Okay, wherever you want to do the further diffusions, in that places we will form the window. So here why we are forming the window, because to form the source and the drain. So if the substrate is a p type, then we are looking for the n type source and the n type drain. That means we have to dope the n type impurities into these regions. Okay, so for doping purpose the two different methods we will use. One is the diffusion and another one is the implantation. Okay, and out of both these two, the ion implantation method of doping the impurities into the substrate is the most preferable one comparing with the diffusions. Okay, so why? Because the ion implantations will properly, if you do the diffusion process, the source will be formed like this, and if you do the ion implantation, the fine diffusions, that means a fine doping can be done. Of course, exactly we don't get like this, but somehow the fine and well depth dopings can be done, okay, into these windows. Okay, so it is one of the advantage of the ion implantation. And how we are going to get, so coming to this question, distribution of implanted impurities by ion implantation method, how it happens. That means with ion implantation method, if you are doping the impurities into the windows, in which format it will take. Regarding this one, okay, I will upload this, I will keep this link in the description box of this video. So this PDF is having the complete information regarding the ion implantation. Okay, so what is the technique we are using here, and what are the advantages and disadvantages. So coming to the advantages, we checked on the precise control of doping levels, what I said previously. So measure the dopant's dose in atoms per centimeter square. Less dopant spread sideways and down. Less dopant spread means, see, diffusion process, the huge spread will happen. That means if it is a required part of the diffusion, this entire part will be diffused. But in the ion implantation, there is no spreadings and all these things. We will get the fine dopings. Okay, so it is a major advantage. And if you see with the help of ion implantation, if you are doping, then the profile will looks like this. It is in the Gaussian curve format. And the supporting equations and each and everything are there in this PDF base. So you please download this PDF and then prepare all these expressions. That means make a note of all these expressions in your notes. Okay, fine. So now coming to this question, the answer can be taken as a Gaussian. Option B is the correct answer. Okay. And while coming to the next question, have a look here. Which of the following is correct for the BJT? Emitter injection efficiency is made close to unity by doping the emitter much higher than the base. Emitter injection efficiency is made close to unity by doping the base much higher than the emitter. Emitter injection efficiency can be improved by use of large emitter band gap than in the base, and emitter injection efficiency is independent upon the doping profile at the laser emitter. If you look at all these options, first of all, you must be clear about what is this emitter injection efficiency. First, let's discuss about that one. Then we will go to the question. Okay. So what is this emitter injection efficiency is that if you take the transistor, okay, if you are taking the BJT, then BJT is having total how many regions? BJT is having the total 3 regions and 2 junctions, right? It is having the 3 regions and 2 junctions. So those 3 regions are emitter, base and collector, and the 2 junctions are emitter junction as well as the collector junction. So while coming to the doping profile, emitter is highly doped, base is very lightly doped, collector is moderately doped. Okay, the doping profile will be like this. Fine. Now, what is this emitter injection efficiency means? Usually, if you take the PNP transistor, PNP transistor, so let's take it is the emitter, base and collector. In the emitter, if the 100 number of holes are there, okay, and in the base N type, let's take the 10 number of electrons are there. Usually, the holes coming from the emitter will enters into the base and then it will enter into the collector and then it will goes to the load. From the collector it goes to the load. So in this process of journey, if the 100 number of electrons are crossing the base, then what will happen? Out of the 100 holes, okay, 10 number of holes will recombine with the 10 electrons in the base. Okay, out of the 100, if 10 holes are recombined, then how many holes will reach to the collector? Only 90 holes will reach to the collector. So from this expression, what we are telling is that generally emitter current is equal to base current plus collector current. It is transistors, whatever the configuration you may take. Okay, emitter current is equal to base current plus collector current. And what is this emitter injection efficiency means? Out of the emitter charge carriers, that is 100, how many number of charge carriers are entering into the collector? Understood? How many out of the emitter, out of the total number of emitter charge carriers, how many number of charge carriers are entering into the collector? That is called as a emitter injection efficiency. That means simply we can take with respect to expression as like this. Emitter injection efficiency is equal to IC by IE. If all the charge carriers of the emitter are entered into the collector region, then my emitter injection efficiency becomes is equal to how much? That is equal to 1. Why? Because if all the emitter charge carriers are entering into the collector, then my emitter injection efficiency, why? Because both these two becomes as equal to same and this will cancel and you will get as a 1. Okay, so if this situation has to be happened, then what about the base current? Base current has to be 0. Okay, but it is an ideal case. We never make the base current is equal to 0. Why? Because we are treating the base as a controlling element of the current in the BJT. Okay, if you make the base as a 0, then what is the necessity of taking the transistor and the controlling elements, all these things? Got it? Fine. So now, to improve, I think all of you understood by this explanation what is the emitter injection efficiency. So if emitter injection efficiency has to be 1, then your base current must be as less as possible. Now come back to the question and read the options carefully one by one. Yeah. Emitter injection efficiency is made close to unity by doping emitter much higher than the base. Got it? If you are making the emitter is much higher than the base, then automatically very few recombination rate will take place in the base. Most number of charge carriers will goes to the collector. Then IC by IE will almost close to unity. So option 1 is the correct answer. And if you go to the option B, emitter injection efficiency is made close to unity by doping the base as a much higher than emitter. If you make the base as a much higher doping than the emitter, then base current will be more. Then automatically, whatever the charge carriers going to the collector will be very, very less. Then how can you get emitter injection efficiency is equal to 1, closely 1? You don't get, right? Next, emitter injection efficiency can be improved by use of large band gap emitter than in the base. Okay, so emitter as a large band gap. If you are making the emitter as a large band gap than the base, means the flowing of charge carriers into the base also will be difficult. So here we can't expect the much conduction here. And here they mention that emitter injection efficiency is independent on the doping profile. It is 100% depending upon the doping profile. So we can't tell that it is independent. Okay. So based upon this one, you can take here option A as a correct answer. Okay. So from this question, all of you have to understand that what is the emitter injection efficiency. Got it? Now let's go to the next question. So the next question is, typical value of the impurity concentration in the tunnel diode. So typical value of the impurity concentration means generally we are having the doping concentrations can be taken as a different, that means low level doping concentration and moderate doping concentration and high doping concentration. Low level doping concentration means we will take 1:10 to the power of 8. What is this 1:10 to the power of 8 means? For 10 to the power of 8 silicon atoms, means silicon, germanium or anything, 10 to the power of 8 semiconductor atoms, we are doping one impurity atom. Got it? We are doping one impurity atom. That is the meaning of this 1:10 to the power of 8. So for 10 to the power of 8 number of silicon atoms, we are doping only one impurity. So it is called as a light doping. And the moderate doping means 1:10 power 6. High doping means we can take approximately 1:10 square. So while coming to the applications, for low dopings means the normal conventional PN junction diodes will come. Moderate dopings means the Zener diodes will come. Okay, Zener diodes will come. And high dopings 1:10 square means the tunnel diodes will come. See, you may check down here. If you are changing the doping concentrations of the PN junction diode, then their applications are also changing. Am I correct or not? If you take the normal PN junction diode, it acts like a rectifier, which converts the AC to rippled DC. Right? If you take the moderate doping concentration, then it acts like a Zener diode, which is acting like a voltage regulation or else a voltage regulator. If you are going for the high doping concentrations, these diodes are useful for oscillators. Oscillators means which converts the DC signals to AC signals, which is quite opposite to this low dopings. Okay, so based upon your doping concentrations, their applications are also changing. So now, while coming back to the question, tunnel diode is a heavily doped diode, so we can take option D is the correct answer. That is 1 part in 10 to the power of 3 parts. Okay. Okay guys, so these are the questions in this present session, and a few more questions. The continuity of the questions we will see in the part 3. Okay, so I'm requesting that please share this video to your groups, to your friends who are preparing for the electronic science examination for the different competitive industries or the organizations. So this channel will be very much helpful to them. So please help to maximize the views of this channel. Okay, So thank you very much guys, and we will meet in the next session. Bye bye.